Welcome to Chemistry with Caroline. In this video, we're going to look at some tips and tricks for solving mechanisms for E1 rearrangement reactions. So the first tip is to identify any unexpected products. And so by that I mean any products that have a different skeletal structure than the starting material. That would indicate to you that a rearrangement had occurred. So we started out with a 5-membered ring here, and here we have a 5-membered ring, and here we have a 6-membered ring, and this is also a 6-membered ring. So it's not enough to just look at the size of the ring. You also have to look at the connectivity of the other substituents. But if I look at my starting material, I have a methyl on that top carbon, and then a methyl and an ethyl on the next door neighbor carbon. And here I have a methyl on the top carbon and a methyl and an ethyl that now has a double bond as a part of it, but on that next door neighbor carbon. So this would be an expected product. It has the same skeletal structure as the starting material, and the double bond is touching, one side of the double bond is touching where the leaving group was on the starting material. So that would suggest to me that there was not a rearrangement there. Whereas my other two products are going to be unexpected products because they have a 6-membered ring, and I started out with a starting material that had only a 5-membered ring. And so those must have been rearrangement products. We'll go to the next slide to work backwards and then start figuring out our mechanism. So for an E1 reaction, the alkene is formed from a carbocation intermediate. So first the leaving group leaves, and in this case, we have a good leaving group in an iodine on a secondary carbon, so it can leave. And that would give me this intermediate. And then I can label so that I can predict what products I would see. So the carbon with the carbocation on it is my alpha carbon. And then the protons that'll be pulled off would be pulled off from next door neighbor positions. So if I go to the right here, I have a carbon that has protons on it. So that would be a beta position. And if I go to the left, I have this carbon over here, beta prime, but beta prime has no hydrogens on it. It's just all carbons. So there won't be any beta prime products because I don't have a proton to pull off there. So I only would see that one product. So if we look at the mechanism for this, once the carbocation has formed, the base can come in and pull the protons off. Those electrons can fold down, and that would give us our final product here, the beta product that we predicted by labeling our starting material. It's the only product where there was a proton adjacent to the alpha carbon. Now the other two products were not formed from this carbocation intermediate. They have a different skeletal structure, and there must have been a rearrangement. To figure out what's going on, what we can do is look for the carbon that is in common between those double bonds, and that is where the carbocation must have been. Now we don't know for sure that these two came from the same carbocation intermediate, but if they did, they would share one carbon between those two double bonds. So in looking at that, you can see that this middle carbon here with the methyl group on it is in both of those double bonds. So that would indicate to me that that is where the carbocation intermediate must have been. So this structure here must have been my intermediate. And if I label that, I'd have an alpha carbon here, right? And then I have two next door neighbors within the ring that are identical. There's a plane of symmetry sort of right down the middle of the molecule like that. So since I already did beta and beta prime, I'm going to do beta double prime and beta double prime on those two neighboring carbons. And then this methyl that's on the outside would be beta triple prime. And with that, I can see that beta triple prime would be right there, and then beta double prime would be right here. So I worked backwards looking for the shared carbon between these alkenes on a rearranged product so I could figure out where the carbocation must have been. So now that I know the precursor carbocation and I know the original carbocation, I just have to show the shift. So I'm almost there mechanistically. All right, so here's our original carbocation that forms when the leaving group leaves, and here's our rearranged carbocation that we know must be the case because we looked at the carbon that's shared between those species to figure out where the carbocation must have been. So the third tip is look at what's different, right? In this case, I'm going from a 5-membered ring to a 6-membered ring. I can also track where substituents are. In my starting material here, I have methyl, methyl, and ethyl, whereas over here I have methyl, methyl, and methyl. So sort of tracking where things go can help me as well. I'm going to number so that we can keep track of where the carbons are. It just helps for clarity. You don't need to number to do this. It's not a part of the mechanism. It's just a part of keeping track. I'm going to start at the carbocation because we're going to do a ring expansion. It's going to accept electrons. So I'll do 1, 2, 3, 4, 5, and 6, just so we can keep track of what's going on. So this molecule is undergoing a ring expansion. Carbon 1 is electron deficient and it can accept electrons. So the bond between carbon 2 and 6 is going to hop out, and carbon 6 is now going to be bonded to carbon 1 in that rearrangement. So if I number again, carbon 1 had the methyl group on it, right? And it had just accepted electrons. Carbon 2 lost electrons. That's this carbon right here. It has the methyl group, but it's now positive. Then you have 3, 4, 5, and 6. Okay, so keeping track of things. And you can see that now instead of having an ethyl, I just have a methyl on carbon 1 because it's become part of the ring and expanded that ring out. So with this newly formed carbocation intermediate, the base can intercept it, pull a proton off of the beta position, fold those electrons down, and that will generate the alkene or one of the alkenes that occurs from that rearranged product. So this has been a look at some strategies to help solve the mechanistic aspect of rearrangement problems in E1 type reactions. If you found this video helpful, please like, subscribe, and share with your friends. Thanks.